Okay, next exercise 13. So here we are given three expressions and we have to write these same expressions using additive notation. They have been written in multiplicative notation where we just don't write the binary operation that is present between two elements. In additive notation, that has to be replaced with the plus sign, and that particularly is done when the operation is commutative, which is the case here because we should also assume that the operation is commutative. So if we rewrite these expressions in additive notation, then a square will be 2a, b cube will be 3b. We already know the meanings of these things. 2a is actually a plus a and 3b is b plus b plus b, and in between them the binary operation is there, which we are now denoting using the plus symbol. So this is part A. For part B, a to the power minus 2 is a inverse a inverse. In additive notation, a inverse is minus a. So that means minus a plus minus a, or 2 times minus a, like that, plus 2 times b inverse c, that means minus b plus c. And finally, like that, part C is 3 times, this is minus 3, that means it's ab square inverse of ab square inverse of ab square inverse of ab square. So that means 3 times inverse of ab square. Inverse of ab square is minus of ab square, that means a plus 2b. It is this part, and the other thing is 2c, that is equal to 0. If you want, you can write e also, but usually when we write additive, when we use additive notation, we denote the identity element by 0. Okay, then exercise 14. For group elements A, B and C, express AB whole cube and AB to the power minus 2C whole to the power minus 2 without parentheses. If we don't use parentheses, then we won't get anything new because of the associative law that is true in any group. You may get rid of parentheses without changing the actual expressions. So we can write like this. Here, however, note that unlike the previous exercise, the binary operation is not necessarily commutative. So in place of AB whole cube, you cannot suddenly write it BA whole cube. Okay, so that is not allowed. Other than that, you can do anything. So the meaning of AB whole cube is AB, 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 but we won't use any brackets. And what about this one? ab to the power minus 2c whole to the power minus 2. This becomes, okay, for the second one, since it's somewhat more complicated than this one, we may have to use some of the properties that we know are true in a group, elementary properties of a group. By definition, this is what? A b to the power minus 2c inverse, and then again a b to the power minus 2c inverse. Now we can take the inverses of these three elements individually. The only thing is that the order of the order in which they are now written, that will be reversed. So first we will have C inverse, then b to the power minus 2 inverse, and then a inverse. We are still using brackets, keep that in mind. We have to ultimately come to an expression that has no brackets, no parentheses. Just like that, C inverse b to the power minus 2 whole inverse a inverse. So we now get rid of the outer brackets, and we have C inverse. If you argue like this, that is b to the power minus 2 is b inverse, and then you take inverse of that product, where you again use the fact that ab whole inverse is b inverse a inverse, you will ultimately see that you have b square here after one or two steps, then C inverse b to the power 2 a inverse. So this is the same element without using any parentheses. Then exercise 15. Let G be a group and H is the set of the inverses of all the group elements. Show that G is equal to H as sets. As sets, they will be equal. Since the inverse of every element in G is again an element in G which is coming from the axioms, the fourth axiom of a group. So H is already a subset of G. Since X inverse belongs to G, for all X belonging to G, we have this. H is a subset of, oh, I forgot whether in this book this symbol represents subset or this symbol represents subset. Like Herstein, I am writing this one. Okay, by this I mean subset, not proper subset. I forgot. I will check it what the actual notation is, but for now you consider this symbol as representing subset relation. Okay. Now we have to prove that the inverse relation is also true. that is G is also a subset of H. For that, let us take any element G belonging to G. Then G is equal to, this is one of the elementary properties of a group. The inverse of any element in a group is the element itself. So that is equal to G, where of course G inverse belongs to G. Now G has the required form to be in H, because it's the inverse of this element in G. This implies that G is also a subset of H. Hence, G is equal to H. That is, if you take the inverses of all the elements in a group and collect those inverses, you are going to get the group back. You won't get anything smaller or anything bigger. Exercise 16. Show that the set five, 15, 25, 35 is a group under multiplication modulo 40. What is the identity element? Of this group? Can you see any relationship between this group and U8? Some ink is needed. Okay, let me write the solution here. Now we are going to form a table. So let me use this ruler so that it looks good. Okay, now the elements we have are these: 5, 15, 25 and 35. Now if the operation is multiplication modulo 40, then you will see that if you calculate these compositions, then you get this. 5 times 5 is of course 25, and 25 mod 40 is 25. 5 times 15 is 75. 75 mod 40 is 35. Like that, you will see that you will get 5 and 15 here. Since multiplication modulo some positive integer is a commutative operation, so the first column will also have the same elements. Okay, then 15 times 35 turns out to be 25. 15 times 25 is 15, and 15 times 35 is 5. So here also we have 15, 5, 15, 5. Then 25 times 25 turns out to be 25, and then 25 times 35 is 35. This is 35 and this is 25. Now from this composition table, how can we conclude that the system is a group? From the above table, we see that this set is closed under multiplication modulo 40. Multiplication modulo 40 is known to be an associative operation. This we have already seen before. Multiplication modulo n, where n is any positive integer, is an associative operation. Okay, now note that the the exercise also asks us to identify the identity element. If you look carefully, the identity element seems to be 25, because when we are multiplying 25 with anything, 25 times 5 is 5, 25 times 15 is 15, 25 times 25 is 25, and 25 times 35 is 35. Also in the other order, that is 25, 5 times 25 is 5, 15 times 25 is 15, 25, 25, 35, 35. So 25 acts as the identity element. 25 is an identity element. Note one subtle thing. What is the identity element of this group? At this stage, we haven't yet shown that the system is a group. So we cannot say the identity element. That's why I am writing an identity element. Only when we have proved that the system is a group will uniqueness of the identity be a fact. Until then, we don't know. Okay, and now the only thing left for us to show is that every element has an inverse. So we just have to identify the inverses. The inverses. Oh, and by that logic, I should not also write the inverses. The elements okay, for 5, inverse is 5, because 5 times 5 is 25, which is the identity. 15 times 15 is 25, 25 times 25 of course is 25, and 35 times 35 is 25. So every element is its own inverse. The elements act as their own inverses. Or if it sounds confusing, you can also write each of these elements acts as its own inverse. Hence, is a group under multiplication modulo 40. Okay, now just like this one, we are let us also form the composition table for U8 and try to see what relationship they have. Okay. Now U8 you already know has 4 elements, 1, 3, 5 and 7, that is the integers less than 8 and relatively prime to 8. But we are going to write them in a particular order which will bring out the relationship between these two groups. Note that the identity element here in this composition table appears there on the third column. So here also we are going to write the identity element in the third column, and the other elements are written like this: 3, 5, 1, 7. So 3 times 3 is 9, 9 mod 8 is 1, 5 times 5 is 25, so this is also 1. 1 times 1 of course is 1, 7 times 7 is 49, 6, 8 ja 48, so this is also 1. 3 times 5 is 15, 8, so that means this is 7, because 8 plus 7 is 15. 3 times 1 is 3, 3 times 7 is 21. In fact, let me just, you can of course do these calculations, and to speed up the process I will just simply write the things: 7, 1, 5, 3, 7, 3, 5, 5, 3, and here we have 7, 7. So you see that if we make this association, that if we associate 3 of this group with 5 of that group, then we associate 5 with 15, 5 of this group and 15 of that group, associate 1 with 25, and we associate 7 with 35. Then the composition tables have exactly the same structure. In what sense? Here you have 3 times 3 equal to 1. There you will have 5 times 5 equal to 25. So it's like a mirror, that is in which the image of 3 is 5. It is something different. Like when we stand in front of a mirror, we see our image. It's just like us, but something else, where the left hand becomes the right hand and vice versa, and such things happen. We are not exactly the same thing. Me and my mirror image are different things, but what I do, my mirror image reciprocates that perfectly. If it doesn't reciprocate that, that means there is a problem. Okay, but jokes aside, so we have this association is like a mirror, where if we are composing 3 with itself and getting 1, then in the mirror world, in that group, 5 is composed with itself and we are getting 25. So 3, 3, 1, 5, 5, 25. So this association not only is not just a random association of the symbols between these two sets, but the association preserves the group structure in the sense that it keeps track of actually what is happening in the first group and translates the same thing in the second group, and the association is able to do that. Okay, that tells us a relationship between these two groups. In fact, in a sense, these two groups are not different groups at all. They are actually the same group. It's just that it's like we have, say, 4 persons in a house who interact among themselves in a certain way, which is captured by this table. Instead of calling this person 3, this person 5, this one 1 and this one 7, we decide to give them some other names, 5, 15, 25 and 35 respectively. Then their behavior or their interrelationship or how they interact among themselves, that is not changed, but according to our new names, these interactions look different, but inside they are the same. That is, when 5 interacts with itself, we get 25, but 5 is just another name given to 3 and 25 is just another name given to 1. So inside what's happening, that is not changing. So the group structure is unchanged, only we have named them differently. Okay, so this way we can identify 2 groups as being essentially the same. The technical term is isomorphism, but I don't believe in this section they have talked about isomorphism. I think it will come later on in some other sections. So that is the relationship. If you want, you can write these things elaborately, but I am ending the solution here itself. So they are essentially the same group. One more thing you can observe is this. There is actually a is that true what I am thinking? If I multiply 3 by 5, no. Yeah, you can in fact change this association a little bit, so that instead of associating 3 with 5, you can associate 3 with 15, 5 with no, that then also it won't happen. No, what I am thinking is not true. Okay, anyway, so this is the relationship. The groups are essentially the same. The next exercise is quite interesting. Exercise 17. Let P and Q be distinct primes. Suppose that H is a proper subset of the integers. That is a group under addition. Under addition, that means under ordinary addition, that contains exactly 3 elements. of the set. So a set of integers is given to us, p plus q, which have been formed from these primes p and q, pq, p to the power q and q to the power p. So it's a set having 5 elements. Determine which of the following are the 3 elements in H. Determine which of the following are the 3 elements in H. So groups of elements have been given: A, PQ, then P to the power Q, Q to the power P. Okay. B, P plus Q, PQ and P to the power Q. C, P, P plus Q and PQ. D, P, P to the power Q, Q to the power P. And E, P, PQ and P to the power Q. Okay. So here we are given a group H, which is as a set, it's a subset of the set of integers, in fact a proper subset, and it's a group under ordinary addition of integers. H is a group under ordinary integer addition, and from among these 5 integers, H contains exactly 3. So what can this among these possibilities, what can those 3 integers be? So for this we make this particular observation. Note that since H is not equal to the set of integers, it's a proper subset, and H is a subgroup under addition. We must have one not in H. Why is that so? Because you see, if 1 belongs to H, then adding n number of ones, where n is a positive integer, you can see that every positive integer also belongs to H, and consequently, since H is a group, every negative integer, which are the inverses of the positive integers, will also be in H, and since H is a group, 0 also belongs to H, so this will make H equal to the set of integers, contradicting the hypothesis. So this particular integer 1 cannot belong to H. Now let us consider these first 3 integers. In these integers, you can see one thing, that since p and q originally are distinct primes, so p to the power q and q to the power p are relatively prime integers. So that means some linear combination of these integers will give us 1. But that linear combination, since if this is the case, if these are the elements belonging to H, then these two will belong to H. So if you multiply these by any integer, that will also belong to H. But why exactly is that so? You see, suppose you have some x in H and you take any integer n, positive, negative or 0, then nx also belongs to H. Why? If n is positive, to prove that nx belongs to H, you just have to consider x plus x plus x n times. That belongs to H because x belongs to H, and that is equal to nx. If n is 0, then this is 0, which is already there in H, since H is an additive group. If n is negative, then nx is minus x plus minus x, etc., plus minus x minus n times. And since x belongs to H, so all these minus x's will belong to H, and so their sum will also belong to H, which is equal to nx. So you see that if p to the power q and q to the power p belong to H, then if you multiply this by any integer, this by any integer, then those products will also belong to H, and hence their sum will also belong to H. But since these two integers are relatively prime, so we can find integers a and b such that 1 is equal to a times p to the power q plus b times q to the power p. But according to our analysis, this thing belongs to H, and then we will get the thing that we are not supposed to get. So that's why A is not a possibility. Okay, so A is not a possibility. That means in these groups of integers, if we find two relatively prime integers, or if we can generate two relatively prime integers, then that is not a possibility. Okay, what about B? In case of B, do we have relatively prime integers? Yes, we have. Okay, let us actually write the reasons. B cannot have okay, at one go we can get rid of A and D. We cannot have p to the power q comma q to the power p belonging to h, since otherwise one is equal to for some integers a and b, where we are of course using the fact that these two numbers, these two integers are relatively prime. I am not mentioning that. Hence, options A and D are ruled out. Okay, A and D are ruled out. What about B? If P plus Q comma PQ comma P to the power Q belong to H, then okay, then q square, which is equal to q times p plus q minus pq, this also belongs to H, because this is an element in H, this is already an element in H, so any integer times this will be an element in H. We have already seen this, and this difference will also be in H. But then again we are in a situation where we have this number and this number belonging to H, but they are relatively prime. But in that case, again 1 is equal to, or we may have to write these combinations again and again. So let us use suffixes a1 and b1. 1 is equal to a2 q square plus b2 p to the power q for some integers a2 and b2. So option B is also not possible. You have now understood how to approach these problems. So what about C? If C is true, now I am not going to write formally. Okay, we just look at the calculation. If P plus Q and PQ belong to H, then what do we have? Then Q belongs to H. Same, then Q square is equal to Q times P plus Q minus PQ belongs to H. Now you have Q square and P, which are again relatively prime. So you will get an impossible situation. So A is ruled out, B was ruled out before, P is ruled out, C is ruled out. So the only possibility is E. Okay, so these are the only possible numbers that can belong to H. Then exercise 18. List the members of these two sets. Belonging to D4 such that x square equal to E. For this, you just look at the Cayley table for the dihedral root D4 that is given in the text. In that table, you look at the leading diagonal elements, that is this diagonal. Those diagonal elements are x square. And you will see that the squares are, each one of them is either the identity R0 or the rotation through 180 degree. And what are the elements whose squares are equal to the identity? There are several such elements that also you can see from the diagonal of the Cayley table. R0 and R180 are among those elements. Apart from that, we have also all the reflections, because if you reflect a square about any axis 2 times about the same axis, you are going to get the thing back in its original position. So reflection about a horizontal axis, about a vertical axis, and about both the diagonals, they are such operations. And among the rotations, only the trivial one is one whose square is identity, and 180 degree rotation is also one whose square is identity, because if you apply it 2 times, then you are rotating the square through an angle of 360 degrees. So that is one complete revolution. Then exercise 19. Prove that the set of all 2 by 2 matrices with entries from R, that is real numbers, and determinant +1. Is a group under matrix multiplication. This exercise is available in many algebra texts in the examples, but for the sake of this solution, let us do it. It's a routine exercise. First, we have to make sure that if we multiply two real 2x2 matrices, each one having determinant 1, then the result of course will be a real 2x2 matrix that we already know, but it should also have determinant 1 that we have to verify. So let A equal to A, B, C, D and B equal to say D, E, F, G, be real 2x2 matrices such that this is the determinant of the first one, this is equal to 1, and that is also equal to the determinant of the second one. Then what about AB? Can calculate AB plus BF. Oh, sorry, we have taken this D here, no? So that's why it was looking a little strange to me. E, F, G, H. We cannot assume that these two elements are equal. They may not be. AE plus BG, AF plus BH, CE plus DG, CF plus DH. Now what about determinant of AB? Either this is a result that we already know, that determinant of AB is determinant of A times determinant of B, or we can verify that here in this case because it's a 2x2 matrix, so the calculation will not be unimaginably large or complicated. AE plus BG times CF plus DH minus AF plus BH times CE plus DG. So we multiply the terms out. AECF plus AEDH plus BGCF plus BGDH minus AFCE minus AFBG minus BHCE minus BHDG. Now there will be some cancellations. Let's identify them. AECF minus AECF. So these two terms cancel each other. Then BHDG, BHDG. So they cancel each other. Now from the remaining terms we try to identify AD minus BC. Note that in this term we have A and D, and along with that we have E and H. Here we have E and H and we have BC and there is a minus sign. So if we take EH common out from this term and this term, then we will have AD minus BC. And from the remaining two, if we take minus FG or GF common out, from the remaining two means from this one. From this one, if we take minus GF common out, then inside we will have minus BC. And from this one, if we take minus GF common out, then we have AD. So AD minus BC. So now the thing becomes AD minus BC times EH minus GF. And both of them are equal to 1. So this is 1 times 1, this is equal to 1. So the product of two such matrices is again a matrix of determinant 1. There is no need to write that, because here we have just simply mentioned in the exercise the set of all 2 by 2 matrices. We haven't given any name to the set, so it's a little bit difficult to, not difficult, but we have to again write the things. So you understand, so the operation is closed. Matrix multiplication is associative. This is a result that we already know, or in this case you can verify also if you want, because we have 2 by 2 matrices, which I am not going to do. The 2 by 2 identity matrix has determinant 1. That is also known. Finally, A inverse. A is that A. A inverse is this. Without the restriction that the determinant is 1, we have the determinant in the denominator. That is why we need the determinant to be non-zero. We are going to use the fact that this is 1, but let us just first write the expression for the inverse. Then minus b divided by AD minus BC minus C by AD minus BC and A by AD minus BC. It's a fact that this matrix is the inverse of A, and it comes from properties of matrices. Okay, based on that we are directly writing this, and this becomes equal to D minus B minus CA. Note that determinant of A inverse is equal to what? dA minus B times minus C, so which is again AD minus BC, and that is equal to 1. So the inverse of A is also a matrix having determinant 1. So that completes all the things, and now we can say that the set is a group. Set of 2 by 2 real matrices with determinant 1 is a group under matrix multiplication, which you can just write, and there the solution ends. We did not have anything else here. Okay. Then 20. For any integer greater than 2, n greater than 2, show that there are at least 2 elements in this group un that satisfy this equation. That satisfy x square equal to 1. We have one and n minus 1 belonging to un such that one square equal to 1 and n minus 1 whole square is also equal to 1. Okay, there are several things here. Okay, but before that, let me just complete the solution, then I will say some things. Since n is greater than 2, we have 1 not equal to n minus 1. So these are 2 elements in un. The squares of both of them are equal to 1. So we have found at least 2 such elements in un. Now the things I was mentioning, note that 1 is in un always. In fact, it is the identity element, and 1 is also less than n and relatively prime to n. But is n minus 1 relatively prime to n? That is one question. Yes, it is. Why? Because you see, you can express 1 as a linear combination of n and n minus 1 with integer coefficients. That's why 1 is the GCD of n and n minus 1, and that's why n and n minus 1 are relatively prime. And since n minus 1 is less than n, so n minus 1 is actually an element in un. Then exercise 21. An abstract algebra teacher intended to give a typist a list of 9 integers. That form a group. Under multiplication modulo 91. Instead, one of the 9 integers was inadvertently left out. So that the list appeared as this. One, 9, 16, 22. 53, 74, 79 and 81. Which integer was left out? And okay, this really happened. So I think it happened with the author himself. Or it may have happened with someone else and the story got out. So we just have to look at the products of these integers and see which one is not appearing in this list. And it turns out that if one takes the product of 9 and 74, modulo 91, okay, that should be kept in mind, then one gets 29. So that is the number that was left out from this list, the missing number. Let G be a group with the property that for any elements x, y and z in the group xy equal to zx implies y equal to z. Note that this implication is neither the left cancellation law nor the right cancellation law, because here we have x on the left and here we have x on the right. So the author is calling this left-right cancellation law. So this whole implication can be said or expressed in words like this: left-right cancellation Oh, I forgot to state what we are supposed to show. Prove that G is abelian. Left-right cancellation implies commutativity. Okay, so if this is true for any triad of three elements, then G must be abelian. Let x and y be any two elements in G. Since x, y is equal to, our aim is to bring an equation or write an equation of this form that we know is true, because then we can use this implication to conclude that y is equal to x. From that we will somehow try to derive commutativity. Now xy can be written as something times x. What is that something? Clearly that something can be taken as this xy x inverse x, because x inverse and x will cancel out, leaving us with xy. So this is a true equation. Since this is true, we must have, so then what does the implication say? It says that y is equal to z. That means y must be equal to this z. xy x inverse. Thus yx is equal to xy x inverse x. This is equal to x inverse and x will cancel out and we will have xy. So xy equals yx. That's why any two elements commute and hence the group is abelian. So G is abelian. Then 23, law of exponents for abelian groups. Let A and B be elements of an abelian group. And let n be any integer. Show that AB whole to the power n equals A to the power n times B to the n. Is this true for non-abelian groups? Some more ink. Since that arbitrary integer n is involved in the claim, so we can prove one part of the claim using induction, and then we can use that part to prove the other part. Note that, or let us start the solution like this. I have to first write the solution. I forgot even that. We first prove this for all positive integers n. For this we apply induction on n. For n equal to 1, this is equal to ab to the power 1, which by definition is ab, but then again ab is a to the power 1, b to the power 1. So in this case the statement is true. assume for some positive integer n, then what about this? This, by definition of such powers or by using the rules of exponent, I mean the more basic ones, not just for abelian groups, this is equal to this. In fact, if you want, you can write 1 here also, or you may wish to also not write, because ultimately ab whole to the power 1 is ab. Now this is the place where we are going to use the induction hypothesis, what we have assumed. So this is a to the power n, b to the power n, a, b. Now use associativity to bring this a with the first two terms. And then again use associativity to write the product like this. Now use the fact that the group is abelian. So in place of b to the power n a, we can write this, and that equals, again use associativity, so we have n plus 1 b to the power n b. Finally use associativity once more, and this gives us, this completes the induction. And hence our claim has been proved for all positive integers. Now if n is 0, that case is also there, it should also be seen, then by definition this is the identity element in the group, which can also be written as identity times identity. This is a to the power 0 and this is b to the power 0. Next, let n be negative, n is a negative integer, then minus n is positive, if n is negative, what is the definition of ab whole to the power n? The definition of ab whole to the power n is, that is the meaning of this is this, ab inverse whole to the power minus n. Now from basic group theoretic property we know that ab whole inverse is b inverse a inverse. But our group is abelian, so in place of b inverse a inverse we can write a inverse b inverse. And now we can use this part that we have already proved for positive exponents. Here now minus n is positive, so it will be equal to this. And this again by definition of such powers is equal to this. So this proves our identity for all integers in positive, negative or 0. And this completes the proof of this identity. However, the question also asks us this extra thing, whether the same is true in non-abelian groups, and the answer is it is in general not true in a non-abelian group. I urge you to come up with an example showing that this is not true in a non-abelian group. That is, you find a non-abelian group in that you consider two elements A and B, and for simplicity you take n equal to 2 and try to show that AB whole square is not equal to A square B square. Okay, so that I want you to do. We will before ending the solution, let's just write this. In a non-abelian group, we don't generally have this. Exercise 24. Socks shoes property. Okay, nice name there. Draw an analogy between the statement and the act of putting on and taking off your socks and shoes. Find distinct non-identity elements A and B. From a non-abelian group. such that A B whole inverse is equal to A inverse B inverse. Okay, find an example that shows that in a group it is possible to have AB to the power minus 2 not equal to this. Oh, sorry, B to the power minus 2, A to the power minus 2. What would be an appropriate name for the group property this inverse equal to C inverse B inverse A inverse? Okay, quite a long exercise. So the first thing is that we have to draw an analogy between this property in any group and putting on and taking off shoes and socks. This I will just explain in words. You do the writing. You think of B as putting on socks and A as putting on shoes, or for example, for our simplicity of thought, let us just think of A as putting on socks and B as putting on shoes, and their inverses as taking off those things. Okay, so it makes sense to put on socks first, that is do A first, and then put on shoes, that is do B after that. You can also try to do it in the reverse order, but that's not what we do generally, unless something is wrong with us. Now, if you have put on socks and then you have put on shoes, and now this whole thing you want to take off, then for that, first of all you have to take off your shoes, and then only you can take off your socks. You can see that thing. So that is the analogy between these two things. That is, if you do something and then do something else on that thing, then to reverse the whole thing, you have to start with the last thing that you have done, reverse that thing, and then after that you reverse the inner thing. That only will give you the intended result. So that is the analogy between this statement and the act of putting on and taking off shoes and socks. Okay, after this we have been asked to find distinct non-identity elements in a non-abelian group such that this happens. For this you can so that socks, shoes, that thing is gone, you write something to explain that. And after this consider the matrices A and B belonging to the general linear group of 2 by 2, that is the multiplicative group of 2 by 2 matrices with real entries where the determinant is non-zero for each one of them. We already know that it is a group with respect to matrix multiplication, and we also know that it's non-abelian. Where A is equal to 1 0 0 2 and B is equal to 2 0 0 3. We have taken A and B to be the so-called diagonal matrices, that is matrices in which the off-diagonal entries, that is entries in places other than the leading diagonal, are all equal to 0. In the leading diagonals, the entries may or may not be 0, but in the leading diagonal we cannot take 0 entry because we want the determinants to be non-zero. We want these matrices to be non-singular, that is invertible. Then let us calculate AB inverse. AB inverse, AB if you calculate, multiplying diagonal matrices is very easy. You just multiply corresponding diagonal entries, that's all. Or if you want, you can actually multiply and see that the matrix again will be a diagonal matrix where the first diagonal entry coming in this way is 2 times 1 2, and the second diagonal entry is 2 times 3 6, and the off diagonal entries are 0. Diagonal matrices are as simple as matrices can get. Their inverses are also very simple. You just have to take the inverses of the diagonal elements. So it's equal to this, and let us also calculate A inverse B inverse. A inverse is 1 0 0 1 upon 2, and B inverse is this. So if we multiply them again, we will see that we have this. So these two are equal in spite of having them from a non-abelian group, and note that these are non-identity elements. None of them is equal to the 2 by 2 identity matrix, but still we have this. Okay, so it can happen in a non-abelian group. After this, we have to find examples of elements in a group that satisfy this non-equality. For that, we go to the dihedral group D4, the group of symmetries of a square. Note that in D4 we have, for this example, if you want, you can use this group also. It is up to you. I have decided to show another group. In D4 one can notice this R90D. To justify these calculations, you just go to the Cayley table for before in the text, and there you have all the things. So R90D turns out to be equal to the reflection H, and H to the power minus 2 is equal to H inverse square by definition of H to the power minus 2, but H inverse H, since H is a reflection, H inverse is H itself, and H square is also equal to R naught. Whereas if you, so this is AB to the power minus 2, now B to the power minus 2, A to the power minus 2, R90 to the power minus 2. This becomes just like HD is also a reflection. Anyway, let's just write all the steps so that there is no chance of confusion. Okay, now D is a reflection, so D inverse is D itself. R90 inverse turns out to be equal to R270. Now this becomes R naught, again since D is a reflection, and R270 square becomes R180. It does not become R naught. So ultimately we have R180, which is not equal to R naught. So this non-inequality is satisfied for this particular thing. And the last part, what would be an appropriate name for the group property? Like for the one having two elements, we could call it, we could make the analogy between putting on and putting off shoes and socks. Like that, you have to think of a situation where you do three things in succession to achieve something. Then to reverse their effect, you have to do the reverse of each such operation, but in reverse order to the original order. I could not come up with any real life analogy, but you can clearly think of something. At present, I cannot think of anything interesting. So I end the, oh, I was supposed to wrap that part. It does not matter. Let us solve one more, and then we will end the video. The other exercises will be solved in the coming videos. So this is exercise 25. Prove that a group G is abelian if and only if AB inverse is equal to A inverse B inverse for all A and B in G. Okay, first assume that G is abelian. Then for any elements A and B in G, this identity is true in any group, not just abelian groups. But now additionally, since G is abelian, this product can be written as A inverse B inverse. So 1/2 is almost trivial. Now conversely, we assume that this identity is there for all elements A and B in G. Then BA whole inverse is equal to B inverse. Oh, okay. What will be the most efficient way of writing it? Sometimes what happens is that if what you are trying to prove is somewhat really easy, you will confuse yourself. I think that is happening to me right now. AB whole inverse is B inverse A inverse by definition, but that is also equal to okay. Then AB can be written as, but for this I then have to use the result of exercise 26. Okay, let us use the result. So AB can be written as AB inverse. Okay, this fact is something we have to prove in the next exercise. So we are prematurely using it. That is not a problem. It will be a problem if in the solution to the second exercise we somehow are using the first exercise. Then the argument will be circular and we will not actually have proved anything. But luckily that will not be the case. So we can use the next result, that is result from the next exercise. So this is equal to this. Now what is given to us is this. AB inverse is A inverse B inverse, inverse of that. But now this is also equal to inverse of this times inverse of this. In this step, we are not using this thing what is given to us. We are just using the ordinary group property that if we take the inverse of a product, that is equal to the product of the inverses taken in the reverse order. So that's what we have used here. And then again using exercise 26, we get BA. We have used the result of exercise 26 here. So we get AB equal to BA, and that's why the group is abelian. So G is abelian. Since we have used exercise 26, let's just solve that also. So we do one more. Here we don't have any abelian group. In a general group, that thing is true. Prove that in a group let G be a group and let A be an element in G. Okay. Let B be equal to A inverse inverse. Then note that B can B is equal to A inverse inverse. So that means what? There is no advantage in calling this element something like B. Instead, let us observe this. Then A inverse is equal to identity by the property of inverses. In fact, from the definition of inverses, an inverse of this element A is an element for which this is true. The other equation is also true, A inverse A is also equal to identity, but we don't need that here. So this is equal to E. But also at the same time, E is equal to A inverse inverse A inverse. Think of A inverse as a single element. If you multiply the inverse of that element with the element itself, then also you will get identity. Now look at this equation. A inverse equal to this. And now we can use the right cancellation law to cancel A inverse from both sides. So by the that's what we wanted to prove. So if you take the inverse of any element in a group, you get the element back. So if you keep on taking inverses, you won't get very far. You will maybe get another element, and after that you will come back to the original element. So let us stop the exercises here. The others will be solved in the coming videos. Okay, lastly I would like to say that I have already said that alongside ring theory we are also going to see group theory from Herstein again. So that those videos will be uploaded on Tuesdays and Saturday. Okay, Tuesday with calculus video, and on Saturday a single video just like this one. Gallian exercises are uploaded on Fridays alone. So that's it for tonight. If you are new to this channel, please consider subscribing, and if you have any doubts regarding these things that we have discussed today or any other thing, then you can always write in the comment section below. So signing off, this is me, Lucifer, from a mathematical room. Have a nice night.